So let's go on with chapter 3. We are looking at 3.2, even though it doesn't say it. We're going to learn a lot of maybe definitions, vocabulary, a lot of stuff about polynomials. So the graphs of them, something called in behavior. The easy stuff is finding zeros by factoring. And then this whole relationship between degrees, real zeros, turning points, and then finally graphing these things here. But let's go for it here. So first of all, definition. By definition, what does a polynomial function look like? If any arbitrary polynomial function, could be degree 1, 2, 3, 4, 5, whatever it is, we say f of x is this a to the sub n, that's what we call it. This is the number in front of x, and this is x taken to any kind of power. And then you sort of go down the list here. So if this was x to the 5th, this would be x to the 4th, then 3rd, then 2nd, 1, and then your constant term over here. Anyways, but if you were to sort of write a polynomial function of any degree, or degree n, this is the way you would write it. Alright, so let's go with some vocabulary here. So the number all the way in front, a sub n, x, then that is called the leading term. That is the one that has the highest degree or exponent on the variable x. The number a sub n is called the leading coefficient, and then a sub 0, that's the one all the way at the end, is called a constant term because it does have an x multiplier next to it. Alright, a constant function, f(x) equal to a, when a cannot be 0, may be written as this kind of polynomial function, and we call it a degree 0. Alright, and then if you have f(x) equal to 0, then we say actually it has no degree whatsoever. Okay, and some special polynomials we talk about, polynomials of degree 3, 4, and 5, they are called cubic, quartic, and quintic polynomials. And of course, if you have degree 2, you have a quadratic polynomial. So we know that. Okay, next thing. What is the whole concept of the domain? The domain of a polynomial is all the real numbers, meaning there are no gaps in polynomials. So whenever you're looking at a polynomial, you understand right away the domain is all real numbers. Okay, but what do we say about a domain? A domain is, first of all, it always has to be a continuous curve. And again, what does a continuous curve look like? Is you can start it with, if you set down a pen or a pencil, you should be able to graph from one side of the graph all the way to the other. Finish it off without lifting off your pen or pencil from the sheet of graph paper. And of course, this is called a discontinuous curve there because it breaks somewhere. Sometime it breaks. That is not considered a polynomial function. This is a continuous curve. Again, considered a polynomial function. Also, a polynomial function is a smooth curve. Not only is it continuous, but we say it's a smooth curve. As you draw it out, first of all, it doesn't have any sharp corners anywhere. All right, as opposed to this right here. As you curve, this is a okay curve, but if it comes to a corner, no longer is this a polynomial. And then again, that's a problem here, that's a problem here. So there are no V shapes anywhere on a polynomial. We call them U shapes. Alright, so let's practice a little bit here with the whole concept of polynomials. First things first, the example problem in the textbook here, let's do that because the practice problems are a little different. So state which functions are polynomial functions. For each polynomial function, you have to find the degree, the leading term, and the leading coefficients. Looking at a, f of x is 5x to the 4th minus 2x plus 7. Is this a polynomial function? And yes, it is. Again, there's no fractions. Notice it goes x to the 4th, x to the 1, and then the constant term. That's called a polynomial function. We also have to find its degree. Its degree is the highest exponent on the x, which is 4. So we say it's degree 4. The leading term is the term that has that highest exponent. So 5x to the 4th would be the leading term. And then the leading coefficient is this number in front of x, which is 5 for this one. All right, g of x, 7x squared minus x plus 1 And then you have this little domain restriction right here. It only goes from 1 to 5. All right, looking at g, this is not a polynomial function. And the reason for it, because it has a domain restriction. Right there. It goes from 1 to 5 only. Polynomial functions always must have a domain from negative infinity to positive infinity. All right, let's go to the practice problems now. The question is this a polynomial function? This is a. So f of x is equal to x squared plus 1 over x minus 1. And right away you should say, no way, Mr. H, that is not a polynomial function. All right, the reason is because it has a fraction, but technically the reason is this right here. Because if you were to raise that denominator up to the top, you have x minus 1 to the negative 1. This little negative 1 right here makes it not a polynomial function. Because polynomial functions, by definition, the exponent has to be a non-negative integer. So it could be 0, 1, 2, 3, 4, 5, but cannot have a negative exponent as part of its factors. Okay, how about b? Let's see this right here. 2x to the 7th plus 5x squared minus 17. Is this a polynomial function? It sure is. Okay, the degree of it is 7, because that is the highest exponent of all the x's. The leading term is the term that has that degree 7, which is 2x to the 7th. All right, and the leading coefficient is going to be 2. It's the real number in front of the x to the 7th. Okay, so there's sort of like the definition sort of stuff there. Okay, now we're going to look at something called the power function. And we're going to use this later on here. So just think of the power function. If you think about, well, you can almost sort of think of it as the leading term. That's what we're going to sort of look at as we look later. But let's just focus just on the power function itself. What does a do to this? And what does the n do to this and to this function here? All right, and if we want to do, maybe like look at an example here. So first and foremost, let's look at something like this. Y is equal to x to the 2nd right here. Something like this. This would be considered a power function. And so what we notice though, first of all is if power functions are of even degree, like x squared, x to the 2nd, x to the 4th, we can put any negative exponent in here, raise it to any even power, and it will still become the same exact function. So we have symmetry with respect to the y-axis. So if f of x is a degree of 2, 4, 6, 8, 10, we will always know right away that it has symmetry about the y-axis. So if we were to graph this x squared, again we would have this. The same thing's going to work for x to the 4th, same thing's going to work for x to the 6th, x to the 8th, any kind of even degree. Next, what happens if it's an odd degree? What happens if it's something like y is equal to x to the 3rd? Well, if you were to plug in a negative and take an odd power, you're going to wind up with a negative in front. So plugging it in as a function itself, taking an odd power leaves you with a negation of the function itself. This means this is an odd function. And odd functions have symmetry with respect to the origin. Okay, now let's look at the graph of these things here. So let's go back to the even function. If n is an even function and a is greater than 0, what's going to happen is going to look like a parabola. Going through 0, 0, and going back up. Again, a good example would be y is equal to x squared. But what happens if a is now a negative number? So again, the good example here, That's the way I think about it. Think of just an example here. Negative x squared. What does that look like? Now it has a, we call this concave down, which means the parabola is facing downward. Okay, that's for the even polynomial. What happens if it's an odd polynomial with a being positive? Again, a good example is y is equal to x to the third. Then you have this shape. Starts low, and it starts going. It goes through 0, 0, and it still keeps on climbing higher and higher. Okay, what's going to happen? And so what we technically say this, we say it starts low, and it ends high. So what happens if a is a negative? Again, the good example here is negative x cubed. This time it's going to start high, and it's going to end low. Now it could do a whole bunch of different stuff here. It could go like this, then it jumps up and down like this, but eventually it's going to wind up going that way. So this is called end behavior. That's the important part. What's happening at the ends? Okay, now let's see how we're going to do this here. Let's look at an example problem again, just to make sure we got it here. So let's say p of x is 2x cubed plus 5x squared minus 7x plus 11. The question is what kind of end behavior is this polynomial going to have? And so technically, mathematically speaking, we have to show that this polynomial p of x is going to be approximately 2x cubed. So what's really happening here is that we're going to factor out the x cubed. If you factor out the x cubed, notice you're going to have all these x's on the bottom, whether it's x or x squared or x cubed. There. What happens as x gets bigger and bigger and bigger? What happens when this is 10,000? 5 over 10,000. That's getting pretty close to 0, is that right? How about, let's say this is a million. 7 divided by a million. That's pretty close to 0. And then this one would be 100 billion. 11 divided by 100 billion, that's going to be a very, very tiny number, very close to 0. So what happens is, as x's get bigger and bigger, we get 3 zeros on our hand. So really what's it saying? It's saying really this right here. It's saying is, as x gets bigger and bigger and bigger, these three terms are going to have less and less an effect on this function. And let's go also, as x gets smaller and smaller and smaller, again, these terms are going to have less and less an effect on this function, and really it's going to model 2x cubed. Okay, so mathematically speaking, let's see if we can show this here. Practice problem number 2. Can you show me that p of x is going to be approximately 4x cubed when x gets very, very large, or when the absolute value of x gets very, very large? Well, here it is. Here's what we're going to do. We have to factor out the greatest degree. So x to the third, the leftovers would be 4 plus 2 over x plus 5 over x squared minus 17 over x cubed. And then what happens for absolute value of x to become bigger and bigger and bigger and bigger? We're going to say 2 over x is going to go to 0. 5 over x squared is going to go to 0. And negative 17 over x cubed will go to 0. Therefore, we're going to have this. X cubed, 4 plus 0 plus 0 minus 0. Approximately. So there it is. We have proved that approximately this function is going to be 4x cubed at the end, or at the end behavior of the graph. Okay, the shortcut, of course. This is just called the leading term test. So why do all that work? Why have to show that as x goes to infinity, x goes to negative infinity? What we technically do, so we forget about that whole mathematical process. We look at the leading term and we say whatever the leading term is going to say, that is the polynomial, or we call the power function that it's going to be close to. Okay, now let's go for it here. So if you have something looks like this, maybe this would be better for an example here. Let's say we have 4x to the 6th plus 3x squared plus 7x plus 4. What we're really going to do is we're going to look at this right here. We're going to say to ourselves first, this is an even function, and the a is greater than 0. And based upon that, you know it's going to start high and it's going to end high. We don't know what's happening in the middle. That's why they got those little dashed lines there. We have no clue what's happening in the middle. But we know in behavior says it's going to start high and end high. Then what happens if I change it up a little bit here? What happens if I have a negative? I don't know. These things are just sort of coming out of my brain here. Negative 7x to the 4th plus 2x cubed minus x plus 12. And again, we can forget about all this stuff here. What's going to happen in behavior is because 4 is an even number, and then because negative 7 is less than 0, based upon these two things here, it's going to start low and it's going to end low, no matter what function it is. I don't know where it's going to cross the y-axis. I don't know when it's going to cross the x-axis, but I know it's going to start low and end low. Okay, next case. What happens if n is odd? So let's give an example here. What happens if we have something like this? 5x cubed plus 7x squared minus 3x plus 4. Again, what we can do is we can just discount all the rest of these here. What's going to happen at the end? This is an odd function. A is greater than 0. So it's going to really resemble a function, this function, 5x cubed. So it's going to start low and eventually it's going to end high. And again, the most simplest function that I can think of that represents this is this function right here, right? This function is going to start low, end high. Okay, let's go for it. N is odd. And now we have a negative for a value. How about, so negative, let's see, 2x to the 5th plus 4x to the 4th minus 3. Let me do another number here. Minus 7x1 plus 14. In behavior, what's happening at the ends on the right and left? Again, we discount all these. We look at this right here. We notice this is an odd function. We notice this is a number that's less than 0. So it's going to, again, it's going to start high. It's going to end low. So that is in behavior in the leading term test. All right, let's apply this real quickly here. Practice problem number 3. It says use the leading term test to determine the in behavior of the graph of that all right, so let's go for it here. So first of all, we say this is case number 2. This is the case where you have a even degree polynomial and you have a negative a value. In this case, what we're going to happen is we're going to start low and end low. That's it. So this is case number 2. All right, the way we'd write it out, if you had to write it out, you would say start low, end low. Okay, and then other textbooks, they might say this. They might say low left and low right. Again, all the different ways you would see it in different pre-algebra textbooks. Okay, we're good there. That big giant part there that we just covered, that is called in behavior of polynomials. Okay, now let's go to how do we find the real zeros of a polynomial. Technically, what we really are finding, you can say this, we're finding the zero of f, you're trying to find the solution of f, you're trying to find the root of f, or you're trying to find the x-intercept. All those are really saying the exact same thing. We say these are equivalent statements. These statements are equivalent. They mean the exact same thing technically. Okay, so let's go for it here. How do you find the real zeros of a polynomial? Let's do the example problem since this was easy enough. Let's take a look at f of x. F of x is x to the fourth minus 2x cubed minus 3x squared. If you look at this here, we're going to have to factor. That's really what we're doing. So we take this polynomial, we factor out the x. As we factor, the x squared. As we factor the x squared, we're left with the x squared minus 2x plus 3. We factor this down even further, and we have ourselves an x squared, x plus 1, x minus 3 as factors. So then the question is, set each of them equal to 0 and solve. This one you have to square root both sides. This you subtract 1, this you add 3, and there they are. The zeros of fx, or the x-intercepts, or the roots, or the solutions of f of x are -1, 0, and 3. Okay, what happens if you have 1, 2, 3, 4 terms? If you have 4 terms, most likely than not, you're going to have to do something called grouping method, or factoring by grouping. Remember that one where you had to spread them out 2 different parentheses? Now they're skipping a few steps here. They spread this out, they factor out the x squared, here they factor out a 1, and they factor the x minus 2 as the binomial factor, again set equal to 0. I do want to show you a little something here though. On this one, x minus 2 is equal to 0, you add 2, we get x equals 2, but this one, x squared plus 1, this one's not going to give you a real number. If it was x squared minus 1, then yes, but x squared plus 1 does not factor, therefore we're stuck here. And the only root that we have is x equals 2. Alright, your job then. Can you find all the zeros of this polynomial? I'll give you a hint. Something called, there are 4 terms here. 4 terms, you might have to do something. Let me give you a little extra time here. Try it yourself. Alright, and back. Let's go for it here. So setting it equal to 0, that's another way you can do it. But here we go. So how about a grouping method? I'm going to put these 2 terms inside the first parenthesis, the last 2 terms inside the second parenthesis, and we see what we can factor out of the first. How about an x squared? Leaves us with 2x minus 3. On the other one here, how about factoring out a 2, which leaves us with 2x minus 3. So the 2x minus 3, 2x minus 3 are common factors, so factoring out the 2x minus 3 leaves us with x squared plus 2. And then at that point here, we're going to set each of them equal to 0 and solve each of those here. Adding 3 divided by 2 gives you 3 halves. The other one is same problem that we had with the example problem. X squared plus 2 does not factor, therefore I'm not going to get any real answers here. So that is a no solution here, but then the final answer would be 3 halves, 1.5. 1.5 is fine as well, whichever. Okay. Let's look at one extra little problem here, something called the intermediate value theorem. So how do we know whether there's actually a 0 or not? If we can't find the 0, how can we still tell that there should be a 0? And so the intermediate value theorem just says this: if you have 2 numbers, a is less than b, and you take the f of a, you put a into the function, then you put b into the function, and you have opposite signs, then you know that there's at least one number in there somewhere. We call it c, for which f of c equals 0. So you know, as soon as you have a sign change, again, kind of like this here. So this would be a, this would be b, And so notice f of x, f of a, that's going to be a positive number. But notice that f of b is going to be a negative number. So if you notice the sign change here, automatically say, whoa, I had a sign change, therefore it had to have crossed 0 sometime. A little example maybe, there it is. A and f of a is on top, b and f of b is on the bottom. There's a sign change between the y values, therefore there has to be a 0 somewhere in there. Or it could be the other way. It could be that f of a was negative, f of b is positive, therefore there is f of z, which has to equal 0. You have to go through a 0 somehow, because it's a polynomial. Alright, also, doesn't mean that there's only one. Could be multiple c values here. So if f of a is positive, f of b is negative, there could be one answer, there could be two, there could be three, there could be a whole bunch of them. We don't know, but we know that there's at least one. And so let's jump to the practice problem here. Show that the function 2x cubed minus 3x minus 6 has at least one real 0 between 1 and 2. Again, really simple here. We do use the intermediate value theorem in calculus as well. It becomes important there. Alright, so all we're going to do is we're going to plug in f of 1. That's really it. F of 1 plugged in. And we should get something like a -7. Then what we do is we plug in f of 2. And we're hoping for a sign change. So I'd say that's going to be 16, that's going to be minus 6, and eventually we get a 4. So is there a real 0 between 1 and 2? Yes. The reason for it, because f of 1 and f of 2 have opposite signs. So then the full answer is, therefore, by the intermediate value theorem, there is a real 0. Okay. And again, this section just sort of introduces the whole concept of polynomials. A lot of vocabulary here, a lot of looking at graphs just to see how it makes sense here. But let's go just looking for zeros. Let's do that first. So how do we find the real zeros of a polynomial function? And we have one little rule here that says if you have a polynomial function that has degree n, so degree 5 or 7 or 6 or 12, you can have only at most n real zeros. And again, just a quick illustration here. How about something like this? If you have x squared, you could actually have no zeros whatsoever. It could just be go down and up and not even go through the 0. It could be that it's going to come down and actually only touch right there. Only touches the 0 here. That's one real 0. Or it could be this function actually goes like this. So at this point there's two real zeros, but there can't be any more than that because you're having an x squared function. Alright, so really what you're going to be doing is you're just going to be factoring, putting them set equal to 0, and solving. So let's try to look at this here. Find the number of distinct real zeros of the following polynomial. Well, if it's already in factored form, then it's easy. All we're going to do is we're going to set each of those factors set equal to 0. X minus 3 is equal to 0, x plus 5 equals to 0. And the only work they've got to do here, we're going to put square root of both sides. We could really put plus or minus there, but it really does not going to matter because 0 is still going to be 0. Alright, subtracting 1 from both sides, you get x is equal to -1. Over here, adding 3. Over here, subtracting 5. And we have 3. Find the number of distinct, there are 3 real zeros, and they are -1, 3, and -5. That's the way the book puts it.